What if everything you thought you knew about time and space was just the tip of the iceberg? Over a century ago, Albert Einstein turned our understanding of the universe on its head with his theory of general relativity, revealing that space and time are not rigid, unchanging entities but dynamic forces that can warp and bend. This isn't just a concept reserved for physics textbook. It's a reality that shapes the very fabric of our cosmos. From the way planets orbit stars to how time itself can slow down or speed up, space-time distortion is a phenomenon that defies intuition yet holds the key to unlocking some of the universe's greatest mysteries. In this video, we're diving deep into 20 astonishing facts about space-time distortion that will challenge your perception of reality and leave you marveling at the wonders of the universe. Get ready to explore how black holes stretch time, why gravity isn't just a force but a curve in space, and what it would mean to travel through a wormhole. Let's embark on this journey together and uncover the secrets of a universe where nothing is quite as it seems. Picture space-time as a vast, stretchy sheet, almost like the surface of a trampoline. Now, imagine placing a bowling ball in the center. The weight of the ball causes the fabric to sag, creating a dent. That's exactly how massive objects like stars and planets warp the fabric of space-time. This isn't just a metaphor, it's the foundation of how gravity works. Contrary to what Newton suggested, gravity isn't a force pulling objects together. Instead, it's the result of space-time itself being curved by mass. Think of it like rolling a marble across that trampoline. The marble will naturally spiral toward the bowling ball, not because it's being pulled, but because the dent in the fabric guides its path. This curvature doesn't just influence how objects move through space, it also affects the flow of time. Near a massive object, time actually slows down, a phenomenon known as gravitational time dilation. It's as if the dent in space-time stretches time itself, creating a kind of cosmic slow-motion effect. This interplay between mass, space, and time leads to some truly mind-bending consequences, which we'll explore next. Have you ever wondered how time might behave in the presence of immense gravitational forces? Let's dive into one of the most mind-bending aspects of space-time distortion, time dilation near massive objects. According to Einstein's theory of general relativity, massive objects like planets, stars, and black holes warp the fabric of space-time, causing time to slow down in their vicinity. Think of it like placing a heavy ball on a stretched sheet. The deeper the indentation, the more time gets stretched and warped. This phenomenon, known as gravitational time dilation, means a clock near a black hole would tick far slower than one in the emptiness of space. To bring this concept closer to home, consider real-world experiments that have confirmed Einstein's predictions. Atomic clocks placed on airplanes, which experience slightly weaker gravity compared to those on Earth's surface, have been shown to tick faster, just as the theory suggests. Even the GPS satellites orbiting our planet must account for these tiny time shifts to keep our navigation systems accurate. It's a subtle effect, but one that underscores how space-time distortion is not just a theoretical idea, it's a measurable reality. Now, imagine stepping into a region where gravity is so intense that time slows to a crawl. What would it feel like to experience time at different speeds? Would a minute near a black hole feel like hours, days, or even years? These questions push the boundaries of our understanding and invite us to explore the extremes of the universe. Speaking of extremes, our next fact will take you even deeper into the bizarre effects of black holes and their role in shaping the cosmos. Picture standing at the edge of a colossal waterfall, where the roaring water disappears into the void below. Now, imagine that same concept, but instead of water, it's space itself being dragged into an invisible abyss. This is what happens near a black hole, an object so dense that it warps space-time to an extreme degree. At the heart of this cosmic enigma lies the event horizon, the ultimate point of no return. Once anything crosses this boundary, even light, the fastest thing in the universe, is trapped forever. It's as if space folds in on itself, creating a one-way street into the unknown. From the perspective of an outside observer, something even stranger happens. If you were to watch an object fall into a black hole, it would appear to slow down as it approaches the event horizon, almost as if time itself were stretching. In reality, time doesn't stop for the object falling in. It's just that the intense gravitational pull distorts our perception of it. Think of it like watching a clock on a spaceship descending into the black hole. From your vantage point, the hands of the clock would seem to freeze, even though they're still ticking normally from the ship's perspective. This bizarre effect is a direct consequence of Einstein's theory of general relativity, which describes how massive objects like black holes bend the fabric of space-time. The closer you get to the event horizon, the more extreme the distortion becomes, until the laws of physics as we know them start to break down. It's a place where the familiar rules of the universe no longer apply, and where the very nature of space and time becomes warped and unpredictable. And this is just the beginning of the strangeness. Near a black hole, other mind-bending phenomena come into play, effects that challenge our understanding of reality itself. Ever wondered what it would be like to be stretched like a piece of spaghetti? Welcome to the bizarre and slightly terrifying phenomenon known as spaghettification, a process that occurs when an object gets too close to a black hole. The gravitational pull near a black hole is so immense that it doesn't just tug on the object, it stretches it out into long, thin strands. Picture an astronaut venturing too close to a black hole's event horizon. The force of gravity at their feet would be exponentially stronger than at their head, creating a tidal effect that elongates their body in the most dramatic way imaginable. It's as if the black hole is pulling them like taffy, turning them into a cosmic noodle. Scientific simulations show this process in stunning detail, with particles being ripped apart and stretched into thin threads as they spiral toward the black hole's center. Theories suggest that nothing, not even the strongest materials, could withstand this kind of gravitational force. It's a reminder of just how extreme the universe can be. And while the idea of spaghettification might sound almost comical, it's a serious and deadly result of space-time distortion. But black holes don't just distort objects. They warp light itself, bending it in ways that seem straight out of science fiction. This leads us to the next mind-bending fact about space-time: how it affects the very fabric of light, creating illusions and magnifying the cosmos in ways we're only beginning to understand. Massive objects in space don't just pull on matter, they bend the very fabric of light itself. This mind-bending phenomenon is known as gravitational lensing, and it's like nature's own magnifying glass. When light from a distant galaxy passes near a massive object, like a black hole or a galaxy cluster, the object's immense gravity warps the light's path, distorting or magnifying the image we see. Sometimes, this distortion creates multiple images of the same galaxy, or even a stunning ring of light called an Einstein ring. The Hubble Space Telescope has captured some of the most breathtaking examples of this, revealing galaxies stretched and twisted into surreal shapes. Think of it like this: if you hold a magnifying glass over a piece of paper, the light bends and focuses into a new shape. Gravitational lensing works in a similar way, but instead of glass, it's the curvature of space-time doing the bending. And this isn't just a cosmic oddity. It's a powerful tool for astronomers, allowing them to peer deeper into the universe than ever before. Now, as we marvel at how light bends around these massive objects, we start to see how space-time itself behaves like a wave, shaping the universe in ways that are both beautiful and profound. Picture throwing a pebble into a calm pond. The water ripples outward in perfect circles, carrying the energy of that tiny impact across the surface. Now, imagine that pond is the fabric of space-time, and the pebble is something far more immense, like two black holes colliding billions of light-years away. That's the essence of gravitational waves, ripples in space-time itself, created by the most violent and energetic events in the universe. These waves stretch and compress space as they travel, carrying with them the fingerprints of their origins. Gravitational waves were first predicted by Albert Einstein over a century ago as part of his theory of general relativity, but it wasn't until 2015 that scientists finally detected them. Using incredibly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, researchers captured the faint echoes of two black holes merging, confirming Einstein's groundbreaking idea. This discovery didn't just validate a theory, it opened an entirely new way of observing the cosmos. Before, we relied on light-visible, X-rays, radio waves to study the universe. Now, gravitational waves give us a whole new sense, letting us listen to the universe instead of just seeing it. What's truly mind-blowing is how these waves reveal hidden aspects of the cosmos. When black holes or neutron stars collide, they don't emit light they're invisible to traditional telescopes. But their gravitational waves carry detailed information about their mass, speed, and even the shape of their orbits. It's like eavesdropping on the universe's most dramatic conversations, uncovering secrets that were once beyond our reach. This newfound ability has already transformed our understanding of black holes, neutron stars, and the very nature of space-time. And it's only the beginning. As detectors become more advanced, we'll likely uncover even more cosmic mysteries waiting to be decoded. Imagine you're driving a car on an endless highway, and no matter how hard you press the gas pedal, there's a speed limit you simply can't break. Now, picture that speed limit as the speed of light, a universal constant that dictates the fastest anything can move in the cosmos. This isn't just a rule for light, it's a fundamental limit for all matter and energy in the universe. The speed of light, approximately 300 million meters per second, isn't just a number. It's woven into the very fabric of space-time itself. But why is it impossible to go faster than light? The answer lies in the way space and time are interconnected. As an object approaches the speed of light, its mass effectively increases, requiring more and more energy to accelerate it further. At the speed of light, an object's mass would become infinite, demanding an infinite amount of energy to keep pushing, a feat that's simply impossible. This cosmic speed limit isn't just a roadblock, it's a cornerstone of causality, ensuring that cause always precedes effect. Without it, the orderly flow of time we're familiar with would unravel, leading to paradoxes where events could seemingly happen out of sequence. To illustrate this, let's revisit the famous twin paradox. Picture two identical twins. One stays on Earth while the other embarks on a high-speed journey through space at nearly the speed of light. When the traveling twin returns, they'll find they've aged much less than their sibling on Earth. This isn't science fiction. It's a direct consequence of how space-time warps at such extreme velocities. Time itself slows down for the moving twin, a phenomenon known as time dilation, proving that the speed of light isn't just a limit but a defining feature of reality. Now, while the speed of light seems like an unbreakable rule, could there be a way to bend or even bypass it? The possibilities might not be as far-fetched as they seem. What if you could hop across the universe in an instant, bypassing the vast emptiness of space? Enter wormholes, the ultimate cosmic shortcut. Theoretical tunnels through the fabric of space-time, wormholes could link two distant points, letting you travel from one end of the galaxy to the other in the blink of an eye. Think of it like folding a piece of paper and poking a hole through it. Instead of traveling along the surface, you're taking a direct route through the fold. While this idea has fueled countless sci-fi adventures, the reality is far more complex. According to Einstein's theory of general relativity, wormholes could exist mathematically, but they'd require exotic matter with negative energy to stay open long enough for anything to pass through. And that's just the first hurdle. Even if we could create or find one, wormholes would be incredibly unstable, potentially collapsing the moment anything entered. Plus, the extreme gravitational forces near them would likely tear anything apart. Still, The idea of wormholes fascinates scientists and storytellers alike, offering a tantalizing glimpse into the possibilities of space-time manipulation. From Interstellar to Star Trek, pop culture loves to imagine these cosmic tunnels, but real science paints a more cautious picture. And while wormholes might make interstellar travel seem within reach, they also raise intriguing questions about how space-time distortion could influence another mind-bending concept, time travel. What if you could travel back in time and meet your younger self? The idea isn't just science fiction. It's a concept rooted in the fascinating world of closed time-like curves. These are hypothetical loops in space-time that, according to Einstein's equations, could theoretically allow for time travel. Imagine following a path that bends so sharply through the fabric of the universe that it loops back to an earlier point in time. Sounds mind-bending, right? But here's where it gets even more intriguing. While the math might allow it, the implications are anything but simple. Take the infamous grandfather paradox. If you traveled back in time and accidentally prevented your own existence, how could you have traveled in the first place? This paradox highlights the deep complexities and philosophical questions tied to the idea of time travel. Even today, physicists are divided. Some argue that closed time-like curves are mathematically possible but physically implausible, while others suggest that the universe might have built-in mechanisms, like quantum mechanics, to prevent such paradoxes. This debate isn't just about equations. It's about our understanding of causality and the very nature of reality. As we ponder these theories, it's worth considering how space-time itself might have played a role in shaping the early universe, setting the stage for the cosmic order we see today. Let's take a moment to consider the very beginning of everything, the Big Bang. This monumental event didn't just mark the birth of matter and energy, it was also the moment space-time itself came into existence. Picture this. At the very start, the entire universe was compressed into an unimaginably small point, infinitely dense and hot. Then, in a fraction of a second, it began to expand, stretching space-time outward in all directions. This expansion didn't stop. It's still happening today, shaping the cosmos as we know it. To visualize this, think of space-time like the surface of a balloon. When you blow air into it, the balloon expands, and every point on its surface moves away from every other point. Similarly, as the universe expands, galaxies are carried along with it, growing farther apart over time. But here's the fascinating part. Space-time isn't just stretching, it's carrying everything within it, like a cosmic river flowing outward. This ongoing expansion has profound implications for the structure of the universe, influencing how galaxies move and how we perceive the vastness of space. Yet, there's still a mystery at the heart of this phenomenon. What's driving this relentless expansion? What unseen force is propelling space-time to stretch faster and faster? The answer lies in something we've yet to fully understand, a mysterious energy that permeates the cosmos, shaping its destiny in ways we're only beginning to uncover. Let's turn our attention to one of the most puzzling forces in the cosmos, dark energy. This mysterious entity is believed to be the driving force behind the accelerating expansion of the universe, a discovery that completely reshaped our understanding of space-time. Unlike gravity, which pulls objects together, dark energy behaves like a cosmic repellent, pushing galaxies apart and stretching the fabric of space-time itself. Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots move farther away from each other. That's essentially what dark energy is doing to the universe, but on a scale that's almost impossible to comprehend. Scientists first detected this accelerated expansion in the late 1990s, and since then, dark energy has remained one of the greatest mysteries in physics. It's estimated to make up around 68% of the universe's total energy, yet we still don't know what it actually is. Some theories suggest it could be a property of space itself, often referred to as the cosmological constant, while others propose it's a dynamic field that changes over time. Despite decades of research, dark energy continues to elude us, leaving researchers to rely on indirect observations and advanced simulations to probe its nature. What's particularly fascinating is how dark energy interacts with space-time. As it pushes the universe to expand faster and faster, it's not just stretching the distances between galaxies, it's altering the very framework of reality. This expansion challenges our understanding of gravity, as dark energy seems to overpower the attractive force that binds galaxies and clusters together. It's a cosmic tug-of-war, with dark energy currently winning on the grandest scales. As we grapple with the mysteries of dark energy, another question arises. How does space-time behave when we zoom into the tiniest scales? From the vast expanse of the cosmos to the quantum realm, the fabric of reality reveals its complexities in ways that continue to astonish us. At the tiniest scales imaginable, the fabric of space-time isn't the smooth, predictable surface we often picture. It's a turbulent, ever-shifting realm known as quantum foam. This chaotic structure challenges everything we thought we knew about the universe's foundation. Imagine space-time not as a flat, unbroken sheet, but as a frothy sea of bubbles, constantly forming and dissolving in a frenzy of activity. This is the bizarre world predicted by quantum mechanics, where the rules of classical physics no longer apply. The idea of quantum foam emerged from attempts to reconcile Einstein's theory of general relativity with the strange behavior of particles in quantum mechanics. At scales smaller than a trillionth of a centimeter, space-time becomes unstable, fluctuating wildly in ways that defy our everyday intuition. These fluctuations are so intense that they could even create tiny wormholes or black holes that pop in and out of existence in the blink of an eye. This chaotic behavior suggests that at its core, space-time might not be continuous, but instead composed of discrete, indivisible units, a concept that ties into theories like quantum gravity and string theory. Quantum gravity attempts to describe how gravity works at these minuscule scales, while string theory proposes that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. Both theories aim to explain the nature of quantum foam and its implications for our understanding of space-time. What's fascinating is that this microscopic chaos doesn't just stay hidden. It could have profound effects on the behavior of particles and the very fabric of reality itself. As we explore these theories, we see how the structure of space-time plays a pivotal role in the behavior of particles, influencing everything from the smallest quantum interactions to the vast cosmic dance of galaxies. This chaotic, fluctuating nature of space-time at microscopic levels opens up a whole new frontier in our quest to understand the universe, one where the very foundation of reality might be far stranger than we ever imagined. Have you ever wondered what gives particles their mass and how that connects to the very fabric of space-time? Enter the Higgs field, an invisible energy field that permeates the universe, interacting with particles in a way that gives them their mass. Picture this field like a vast ocean of molasses. As particles move through it, they slow down, gaining mass in the process. This interaction isn't just a quirk of physics, it's a fundamental part of how our universe works. In 2012, the Large Hadron Collider made a monumental discovery: the Higgs boson, the particle associated with this field. This breakthrough confirmed the existence of the Higgs field and deepened our understanding of how mass is created. It's like finding the missing piece of a cosmic puzzle, one that helps explain why the universe is structured the way it is. But the implications go even further. This discovery sheds light on how the Higgs field interacts with space-time, influencing the very framework of reality. As we explore this connection, we're led to another intriguing piece of the cosmic story: the cosmic microwave background, the faint echo of the Big Bang that holds clues to the universe's earliest moments. The cosmic microwave background radiation is like a photograph of the universe's baby picture, a snapshot frozen in time from when the cosmos was just a few 100,000 years old. This faint glow, discovered in the 1960s, is the afterglow of the Big Bang itself, and it's one of the most important pieces of evidence we have about the origins of our universe. Think of it as the universe's first selfie, capturing the moment when space-time began to cool enough for light to travel freely for the first time. By studying this radiation, scientists have been able to measure the universe's age, approximately 13.8 billion years, and determine its composition, including the amounts of dark matter and dark energy that shape its structure. The tiny fluctuations in the cosmic microwave background reveal the seeds of galaxies and clusters we see today, showing how space-time itself was stretched and distorted during the universe's rapid expansion. It's as if we're reading the cosmic version of a history book, with every ripple and pattern telling a story about the forces that shaped our reality. Now, if the cosmic microwave background is like a photograph, it's also a reminder of how interconnected space-time is with everything we observe. This ancient light doesn't just tell us about the past, it hints at the future. As we peer deeper into these patterns, we begin to ask bigger questions. For instance, could the properties of space-time we see in our universe also exist in others? This leads us to the fascinating idea of the multiverse, where space-time might take on entirely different forms in other unseen realms. What if our universe isn't the only one? Picture a cosmic tapestry where countless universes, each with its own unique space-time fabric, exist side by side. This is the heart of multiverse theory, a concept that stretches the boundaries of our understanding. Rooted in the complexities of quantum mechanics and string theory, this idea suggests that space-time isn't uniform across all realities. In some universes, time might flow backward, or gravity could behave entirely differently. The implications are staggering, but so are the challenges. How do you prove something exists beyond the observable limits of our universe? For now, the multiverse remains a tantalizing possibility, a cosmic puzzle that pushes scientists to rethink the very nature of reality. And as we ponder the mysteries of these parallel worlds, we're led to an even bigger question. Could space-time hold the key to unifying the laws of physics across the multiverse? The concept of unifying space-time with quantum mechanics remains one of the most ambitious scientific endeavors in modern physics. Picture this: space-time, as we understand it from Einstein's theory of relativity, is smooth and continuous, like a vast, unbroken fabric. On the other hand, quantum mechanics reveals a world of particles and forces that behave in discrete, unpredictable ways. Bridging these two frameworks is like trying to weave together two completely different textiles, one seamless, the other fragmented. Theories like loop quantum gravity and string theory are at the forefront of this quest. Loop quantum gravity suggests that space-time itself is made up of tiny, indivisible loops, while string theory proposes that everything, including space-time, is composed of vibrating strings. Both approaches aim to reconcile the smoothness of space-time with the quantum world's granularity, much like blending threads of different textures into a single, cohesive tapestry. While these theories are still being tested, their potential implications are profound, offering a glimpse into a unified understanding of the universe. As we ponder these grand ideas, it's worth remembering that space-time isn't just an abstract concept. It shapes our everyday reality, from the way we experience gravity to the way we measure time. This brings us to the next fascinating fact about how space-time influences even the most ordinary moments of life. Did you know that the effects of space-time distortion are silently shaping your everyday life, even if you can't see them? Take something as commonplace as using GPS on your phone. Those satellites orbiting Earth are constantly sending signals to help you navigate. But here's the twist: they're also experiencing time at a slightly different speed than we are on the surface. Because they're farther from Earth's gravitational pull, time ticks faster for them by a tiny fraction. Without corrections for this time dilation, your GPS could be off by several miles in just a matter of minutes. It's a subtle yet crucial adjustment that ensures your navigation apps work accurately. Another fascinating example is the way time slows down near massive objects like Earth. If you've ever stood at the base of a tall building and compared your watch to someone's on the top floor, you'd find that time moves slightly faster for them, though the difference is so small it's practically undetectable without precise instruments. These everyday phenomena are proof that space-time isn't just a grand concept reserved for black holes or distant galaxies. It's woven into the fabric of our reality, quietly influencing the technology we rely on and the world we inhabit. But space-time's reach extends far beyond Earth. In the search for exoplanets, worlds orbiting distant stars, scientists use the warping of space-time to detect these celestial bodies. When a planet passes in front of its star, it causes a slight gravitational lensing effect, bending the star's light and revealing its presence. This technique has opened up a new frontier in astronomy, allowing us to discover thousands of exoplanets and learn more about the universe's incredible diversity. Space-time isn't just a cosmic curiosity, it's a tool that helps us explore the vast unknown. Here's the next section of the script, tailored to your requirements. One of the most fascinating applications of space-time distortion is its role in the hunt for distant worlds beyond our solar system. Imagine space-time acting like a cosmic magnifying glass, bending and focusing the light from faraway stars. This phenomenon, known as gravitational microlensing, occurs when a massive object like a star or even a black hole passes between us and a more distant star. The gravity of this object warps space-time, causing the background star's light to curve around it and briefly brighten. If the foreground object happens to have a planet orbiting it, that planet can leave its own tiny imprint on the light, revealing its presence to astronomers. This method has been incredibly successful in uncovering thousands of exoplanets, many of which would have remained hidden using other techniques. Microlensing is particularly effective for spotting planets that are far from their host stars or those in regions where traditional detection methods struggle. It's like finding a needle in a haystack, except the needle is a distant planet and the haystack is the vast expanse of the galaxy. But what's truly exciting is the future of this research. As our technology advances, we're poised to discover even more exotic worlds, some of which might resemble Earth in ways we've never seen before. The study of space-time distortions isn't just about understanding gravity. It's about unlocking the secrets of the universe and answering one of humanity's oldest questions: are we alone out here? And as we continue to explore, who knows what other surprises space-time might have in store for us? As we peer into the future of space-time research, it's clear that humanity is on the brink of unlocking some of the universe's most profound secrets. Advanced technologies and ambitious experiments are paving the way for discoveries that could reshape our understanding of reality itself. At the forefront of this exploration is the James Webb Space Telescope, a marvel of engineering designed to observe the earliest galaxies and shed light on the cosmic conditions that shaped space-time billions of years ago. By capturing light from the dawn of the universe, Webb offers a glimpse into the past, helping us piece together how space-time evolved over eons. But our tools don't stop there. Next-generation gravitational wave detectors, like the proposed Einstein telescope, promise to take our understanding to new heights. These ultra-sensitive instruments will detect ripples in space-time with unprecedented precision, allowing us to study phenomena like colliding black holes and neutron stars in exquisite detail. Gravitational waves are like cosmic messengers, carrying information about the most violent and energetic events in the universe. With these detectors, we're not just observing the universe, we're listening to it. The potential for groundbreaking discoveries is immense. From uncovering the true nature of dark matter and dark energy to testing Einstein's theory of general relativity in extreme environments, these advancements could answer questions that have puzzled scientists for decades. Imagine the possibilities: confirming the existence of wormholes, mapping the curvature of space-time around supermassive black holes, or even detecting signals from other dimensions. The future of space-time research isn't just about understanding the cosmos, it's about redefining our place within it. As we stand on the edge of this new frontier, it's impossible not to reflect on the profound implications of space-time distortion. These discoveries don't just enrich our scientific knowledge, they challenge us to rethink the very fabric of reality. What once seemed like science fiction time travel, warp drives, parallel universes may one day become grounded in scientific truth. The journey to understand space-time is far from over, but with each new discovery, we come closer to unraveling the mysteries that bind the universe together. Space-time distortion isn't just a scientific concept, it's a profound challenge to how we perceive reality itself. Think about it. Time and space, the very fabric of our existence, aren't fixed or absolute. They bend, stretch, and warp, influenced by mass, energy, and motion. This idea shatters our everyday understanding of the universe, forcing us to question everything we thought we knew. As Albert Einstein once said, reality is merely an illusion, albeit a very persistent one, and space-time distortion is the ultimate reminder of that illusion. Philosophers and scientists have grappled with these implications for decades. The great philosopher Immanuel Kant argued that space and time are frameworks of our perception, tools our minds use to make sense of the world. But space-time distortion suggests these frameworks are far more malleable than Kant ever imagined. Similarly, physicist Carlo Rovelli has described time as a network of relationships, emphasizing that it's not a universal constant, but something that changes depending on where and how you observe it. These perspectives force us to reconsider not just the universe, but our place within it. What does this mean for our understanding of existence? If time can slow down or speed up depending on gravity or velocity, does that mean our experience of life is also relative? If space can stretch, does that mean the distances we perceive aren't as fixed as they seem? These questions blur the line between science and philosophy, inviting us to think deeply about the nature of reality. As Stephen Hawking once remarked, the universe doesn't allow perfection, maybe imperfection. The bending, twisting, and warping of space-time is what makes the cosmos so endlessly fascinating. These insights remind us that the universe is far stranger and more complex than we often assume. From the bending of light around massive objects to the way time crawls near a black hole, space-time distortion reveals a cosmos that's dynamic, interconnected, and profoundly mysterious. It's a reminder that science isn't just about answering questions. It's about uncovering deeper mysteries that challenge our very understanding of existence. And as we close this journey through the wonders of space-time, let's take a moment to reflect on the incredible insights we've explored together. From the colossal warping of space-time around black holes to the bizarre, foamy fabric of the quantum realm, our journey through these 20 astonishing facts has revealed just how profoundly space-time distortion shapes our universe. We've explored how massive objects like stars and galaxies bend the very fabric of reality, creating phenomena like gravitational lensing that allow us to peek into the cosmos in ways once thought impossible. We've delved into the peculiar effects of time dilation, where time itself stretches or compresses depending on speed and gravity, proving that time is far from the constant we perceive it to be. And who could forget the mind-bending concept of wormholes, hypothetical tunnels through space-time that could, if they exist, connect distant parts of the universe in an instant. These ideas don't just challenge our understanding of physics, they invite us to rethink our place in the cosmos. Space-time distortion isn't just a scientific curiosity, it's a gateway to profound philosophical questions about the nature of reality, time, and existence. As we've seen, even the empty vacuum of space isn't truly empty but seethes with quantum fluctuations, hinting at a universe far more dynamic and mysterious than we've ever imagined. As Carl Sagan once said somewhere, something incredible is waiting to be known. And indeed, the more we uncover about space-time, the more we realize how much remains hidden. So, what do you think? How do these discoveries about space-time reshape your view of the universe? Share your thoughts in the comments below. I'd love to hear your perspectives. And if you're as captivated by these cosmic wonders as I am, don't forget to subscribe for more deep dives into the mysteries of the cosmos. After all, the universe is far stranger than we can imagine. What other secrets does space-time hold?